All right, so let me start by asking you, who has heard of and or seen Venn diagrams before? Okay, about half of you have. Venn diagrams are used for lots of things, and they're used at various points that you might not have realized that they're used. So my daughter last year in second grade used Venn diagrams at school. Not for what we're using them for, but they know what they are, much younger than probably what you or I did. And those of you who don't know what they are still yet, then you just know that when you see that niece or that nephew and they know what you're going to be able to say, yeah, I know Venn diagrams now. Okay, it's good stuff. All right, so let's talk about what they are. So first of all, a Venn diagram is a picture. That's what it is. It's a picture of a rectangle. That rectangle or that box is the universal set U. And we represent sets that are inside of that with circles. And those circles, we can give other names, whatever we'd like. So I'm going to call it set A. So this is a set. We talked about sets in the last chapter, or last section of this chapter. And it is inside of a universal set U. So the universal set U could be anything. It could be a whole bunch of numbers. It could be people. It could be whatever we'd like. And then the A inside of it is a sub-collection. It's a smaller grouping of something in that category. So this is kind of like what we did when we drew the picture last time of the big rectangle, and we split it to irrational and rational. And then inside of the rational, we drew another rectangle, another rectangle. We didn't do circles. I could have. But just for the sake of where my spacing was, rectangles kind of worked a little nicer. But that actually would have been a version of a Venn diagram. Okay? So let's take a look at a couple of different things. One is the idea of complement. And this is misspelled. I see right now. There's actually an E here, not an I. All right, so this is not complement like, hey, I really like those shoes. It's not what this means. But there is a little bit of something that's kind of like that in it. So any set A within the universal set, and you saw the picture on the slide before, the complement of A, written A with a little apostrophe kind of prime notation, you may have seen it in some math class before. This is all elements that are in the universal set, but they're not in A. So from a picture point of view, if you have the same picture we had before, and this is set A and this is set U, then A complement is the space outside of the circle, but still inside the rectangle. So inside the rectangle, outside the circle. That's set A complement. We read A complement. Just kind of an FYI, if you've ever seen or heard of complements before, you may be more familiar with a different notation. A complement written the way your book does, like this, has another notation that would look like A with a little C, kind of like as a subscript up high, kind of like an exponent. Or some books will write it as the A with a bar on top of it. There's another book that I teach out of that uses that last notation. It's a class I'm teaching right now, in fact. So I don't care really which one you use. Your book's using the first one, but I just want you to be aware of the fact that this isn't sort of like, a convention that's always used. There's several different conventions. Now, the parallel that you may have thought of, so I told you this isn't like a compliment like, hey, I like your shoes. But, so perhaps you've heard someone say before in reference to their husband or wife or somebody they're dating that we complement each other. Have you heard that phrase? That's actually along the lines of what this is talking about. When somebody says we complement each other, it doesn't mean we give each other compliments, right? It's not what somebody means when they say that. It means that somehow they have aspects that you don't, and you have aspects that they don't, right? This is what happens with me in technology. So if you'd been in my class yesterday when I was using the iPad, I was having all sorts of problems, and I gave up and I used the chalkboard, all right? So I have this problem at home sometimes. And my husband will ask me questions like, well, have you turned the computer off and tried to turn it back on? Or have you tried this or have you tried that? And some of the time now I'll actually try those things. But most of the time when we were first married, I would be like, well, no. Because in all honesty, right, if I could do everything my husband can do and he could do everything that I can do, then one of us is not necessary. Right? Because you'd be the same person. That would be dumb, right? So this idea of complementing each other is this idea of this picture. That there's aspects inside that are not outside and vice versa, okay? All right, so we're going to take a look at an example. This U is the universal set, so it's the big rectangle. And inside my big rectangle, I have elements that are the numbers 1 through 10. And what we want to do is we want to find the complement of each set. So let me give this first set, number 1, a name. It may have a name on your paper. I think it does. A? No? Okay, well, let me give it a name A so that I can actually use some notation. I want to find a complement. So the first thing to realize is it's a set, which means it needs to be in parentheses. Or not parentheses, but the curly braces, just like before. And then I want to list everything that's in the universal set that's not listed in set A. Somebody tell me one item. 8. Somebody tell me another one. 5. What else? 6. 9. That's all of them, right? Okay. So this is the set A complement. And I'm actually glad you listed 8 first. No, it's good, because it's good to realize it doesn't matter what order we put them in. So if you want to put them in order, great. If you don't put them in order, it's no problem. Okay? So this will work. Number 2 is sort of like a trick question. It isn't, but I want you to realize what's going on. So I'm trying to find U complement. Okay, so the very definition of complement says I want to find everything in the universal set that's not in the set that I just listed. So I need everything in the set 1 through 10 that's not in the set 1 through 10. That's the null set. We encountered that last time, or a couple times ago actually, Monday. So you can either list this as the empty set like that, or you could list it as the empty set like this, right? That doesn't look very good. Let's try one more time. Better? It doesn't matter which one you do. But the complement of the universal set is the empty set, right? The complement of having everything is having nothing. But likewise, the complement of the empty set would be the universal set, everything, right? So these are complements of one another. Everybody with me? Okay. All right, another idea, and we've already seen a picture of it, is the idea of a subset. And we actually talked about it, but I didn't define it last time too. A subset is simply a set where every element in it is an element of the larger set, or at least potentially larger. So A is a subset of B if every element in A is an element in B. All right, so picture-wise, you got this going on. And this is what I did when I did those nesting squares or rectangles with the number systems last time. Do you guys remember the squares? Rectangles, they were one inside of the other, right? Natural number, whole number, integer, right? They were one inside of the other. They were subsets of each other. Well, the smaller one was a subset of the larger one, okay? And that's what we have here. Okay, so we have another definition of set equality. We encountered this idea last time, and this really isn't an alternate definition as in it really is different. It's just notationally it looks different. So if A and B are subsets, then A is equal to B. If A is a subset of B, right, that means everything in A is in B. And B is a subset of A, which means everything in B is in A. And my statements where I said, which means, was exactly what we wrote down last time. All right? So this notation, A is a subset of B, and B is a subset of A. Those were the two conditions when we wrote them down last time. We had a condition 1, a condition 2. Both those conditions have to be true. Now, I haven't written down the notation for this yet, so let's do that. If A is a subset of B, the notation for that looks like this. Okay, so it's kind of sloppy, but it looks sort of like a C or a sideways U, and it's got a line underneath it. And we read that A is a subset of B. Another phrase that you'll sometimes hear me say, because it means the same thing, is A is contained in B. And from a picture point of view, does that make sense? Okay, so A is contained in B. And what it actually means is every element in A is an element in B. I haven't said something yet because it's on the next slide, but we also have an idea of a proper subset. Okay, so there's two phrases here. There's the phrase, or two words, the word proper and then the word subset. So first thing is, if it's a proper subset, first of all, it had to be a subset to begin with. Okay, so that sounds good, right? So we're not going to put the word subset into something that wasn't already a subset. The issue about it being proper has to do with the fact that it's not actually equal to the set itself. So it's a proper subset if it's a subset, but it's not equal to the other set. I.e., it is a smaller set. That is, A is smaller than B. So if the sets are the same set, exactly identically the same, then they're subsets of each other. I mean, that's just the definition. Everything in one's in the other. So it seems sort of weird to say they're subsets of each other because they're equal, but by definition, they are subsets of each other. If it's a proper subset, however, they can't be equal to each other. Okay, it's actually smaller than the set we started with. All right. Can I go to the next slide, or are we still writing? I don't want to rush, but are we okay?
What's the notation?
Oh, thank you, Tyler. The notation looks like this. You do need that. What's different? There's no line underneath it. So you might, to yourself, think, I've seen that idea of a line versus not a line underneath something before. Where have you seen it? Less than or equal to, and versus less than, right? So think with me, let me use an example. We can't say 7 is less than 7, right? That would be a false statement. Okay, so they can't be equal to each other and not have the equals underneath. But we could say 7 is less than or equal to 7, and that would be true. It seems awkward to say, but it is a true statement, right? It's kind of like the idea of subsets. Subsets could actually be equal to each other. It seems strange to call them subsets, but by definition it would be okay. Same thing here. It seems strange to say 7 is less than or equal to 7, but technically it's a true statement, right? It's the same idea. Okay, so we're going to do an example, 3 examples of this. Our goal is to write one of 4 things in the blank. So this is kind of like a multiple choice activity, right? You have to pick one of the 4. The first option is you can write the proper subset notation. The second option is you can write just the plain old subset notation. If both items could go in the blank, you're going to write the word both. But if neither one fit in the blank, you're going to write neither. Okay, so multiple choice, 1 of 4 answers. All right, so there's 2 questions to ask yourself when you're making this decision. Question number 1 is the set on the left have everything in it in the set on the right? Is every single one of these things over here also over here?
Yes.
Okay, so that's what we're going to ask first. Just a second, Tyler. We're not going to do one of them. Just let me say that's first. Question number 1. Question number 2 you have to ask yourself is the set that's on the left smaller than the set on the right? So those are the 2 questions you have to ask yourself for each one of these in order to make the decision. So Tyler already answered my first question on the first one. Okay, number 3. Is everything on the left also on the right? Yes. If that's the case, then that means we could use one of these 2 notations. We don't know which one yet, but it's one of those 2. Okay, or there were both potentially. In other words, we sort of have eliminated the neither option because everything over here is over here. Second question, is the set on the left smaller than the set on the right? Yes, it is. Which means what could go in that blank? The one without the line could, right? The one without the line means that the one on the left is smaller than the one on the right. Okay, so this notation, let me jot this down. This notation has a smaller connotation to it. The one on the left is smaller than the one on the right. Yes?
Is it always going to be the case where the small one's going to be on the left if, like, 4 is
That's a good question. So the notation always has the subset notation moving to the right-hand side. It's always going to open to the right. So the questions are always going to be asking you to move from the left to the right. So you're always going to be comparing it in that same order. Yeah, that's a good question, because that's different than the less than or equal to ones, right? Because we could do the order the other way around with that example, but this is something a little different. Just notationally, we're going to move from left to right. Okay, so is it smaller? Yes, which means the first symbol would work. The second symbol, the one with the equal to underneath, means is it a subset? That was my other question. Is everything on the left in the right? Yes. So the second one with the line underneath it, that one also would work. So what goes in the blank? Both. We could use both of those symbols between this and they would be correct. The first symbol, the fact that it's smaller. The second symbol, the fact that it's a subset. Both of them will work in this blank. Let's look at number 4, asking ourselves the same questions. And it doesn't matter which order we ask them in. So let's change the order. Let's talk about smaller issues first. Is the set on the left smaller than the set on the right? No, it is not. So since it is not smaller, that means that that first symbol, the contained symbol without the line underneath it, is not a possibility for us. That also means that the possibility of both is not a possibility, right? So in one fell swoop, we just narrowed our choices down to 2 choices. Second question is everything on the left also on the right? And that answer is yes. What should go in this blank? The subset symbol with the line. Okay, let's look at 5. We'll still go, well, let's do the smaller one first again, too. Okay, set number 5. Is the set on the left smaller than the one on the right? No, which tells us what's not going to work. The first symbol without the line, the C symbol without the line, and the word both. We could eliminate both of them, just like the last one, right? Is everything on the left also on the right? No. So what goes in the blank? Neither. Does this make sense? Okay, so if you haven't already written this down, it's okay, but you might want to write down the note to yourself about these 2 questions. Because these 2 questions, if you ask yourself these 2 questions and answer them every time, they tell you which one to pick, right? Yeah. All right, cardinality. Okay, so cardinality, this is the question you asked me about, Alice. So no wonder we got some blank stares from some people in class because we haven't talked about it yet. Cardinality. Well, at least from this perspective. Sorry, this is a different cardinality. We talked about cardinality last time as in the number of items in a set, like the one Alice asked us about here. This is actually the cardinality of the number of subsets. Okay? So this is a formula, let's say it that way, for how you figure out the number of subsets that a set has. And I'd like for us to do an example of one so you can see why in the world a formula would be nice to have. Okay? So we're going to do an example. In fact, I'm going to switch to a different slide so we can see it. We'll come back. If you didn't write anything down, it's okay. I promise I'm going to come back. All right? We're going to do an example of a set. Our set A is going to have the items in it 1, 2, and 3. And what we're going to do is we're going to list all possible subsets of this set. Okay? The first one I'm going to list is one that you might not have thought of, so I'm going to start with it. The first subset is the empty set. Okay? I know it sounds kind of weird, but think with me. In order to be a subset, it means everything that's in the set is in the larger set. So what's in the empty set? Nothing. So by default, that set, every element in it, of which there are none, is in the other set. Right? It's a semantics thing, right? It's a language deal. It's not a mathematical operation per se we're talking about. It's the language we're talking about. By default, everything that has nothing in it is in the other one. Okay? The empty set, it's a subset of everything. So there's the first one. The next one that I'm going to list is the subset with the number 1 in it. Is everything in that set in the set A? Yes. So somebody tell me another subset. 2. Another one. 3. Okay, so these are the 3 subsets that have 1 element in them. Somebody tell me another subset.
1, 2.
1 and 2. So if there's these, again, everything in that set is in the set A. What else? 2, 3. Somebody else said something. 3 and 1, or 1 and 3, either way, yep. There's one more. 1, 2, 3. Again, remember the language. Everything in that set 1, 2, 3 is in the set A. Right. They're equal. I get it, but everything still follows the definition, so it is a subset of itself. How many were there? 8. There are 8 subsets when you have 3 elements. Do you want to do this if you have 7 elements? No, because you got to do all combinations of 0 elements and 1 element and 2 elements and 3 and 4 and 5 and 6 and 7. This will take a while, right? So I would much prefer to have a short, nice little concise formula that shows me if I'm asked for how many subsets there are, I can just plug a number into a formula. And that's what this, here we go, gives us. So take a look. This says if you have n elements in your set, then you will have 2 raised to the nth power number of subsets. Let's check to make sure it worked. Our set A just a moment ago was the numbers 1, 2, 3. What was n? How many elements are in that set? 3. So what is 2 raised to the 3rd power? 8. Right? That's the number I got when I wrote them all out longhand. So just to make sure everybody's with me, what would you do if you had 7 elements? How many subsets would there be? 2 to the 7th, whatever that works out to be, right? So then you could grab a calculator if you prefer, raise 2 to the 7th, and you'd be able to tell me that actually that's 128. I don't know about you, but I don't want to write out 128 subsets. I could do it. It would take a long time. Wouldn't be very efficient, right? All right, proper subsets. Let me go back to this other slide. I promise if you're still writing, we'll go back to that one. Proper subsets, remember, means every subset that I already have except what? You got it. Kaylin, right? Okay. This one is equal to the set I started with. So it's a subset, but it is not a proper subset. So how many proper subsets do I have? 7. In essence, I have exactly 1 less. So when we're thinking about the formula for how many subsets I have that same 2 to the n that I had before from up here, and I just have 1 less of them. So my proper subsets is the same number of subsets that I had before minus 1. And of course, if you were to do this on the one that we just did, you would again get 2 to the 3rd minus 1 would be the 7 subsets that we had from before on our example. Okay? Okay, we have an example, 2 examples. We're supposed to find 2 things. A, the number of subsets, and B, the number of proper subsets for each set. So in order to do that, what do I have to identify first? The number of items in the set, right? Okay, so how many items are in set A? In other words, what is in? 5. So part A, I'm asked to find, is the number of subsets. So how do I do that?
2.
The other way around. 2 to the power of 5. Does anybody know what 2 to the power of 5 is? It's 32. And if you don't, you grab a calculator and it will tell you, right? So there are 32 subsets. Once I find the number of subsets, do I really need the formula per se anymore? Not really. How many proper subsets are there then? 31. Just take one off. Now B's a little different because B doesn't list a bunch of symbols like part A did, right? or no, letter A did. Set B says x such that x is an odd integer between -9 and 4. So what would you like to do? Sure, we could list them out, right? Yeah, we could. So let's do that. What would this set be in terms of the numbers that I get to include? Okay, so it's a question. Do we get to include -9? No, we're not going to. Why not?
Because it's between.
Yeah, it actually used the word between. So the word between means we're not going to include the endpoint. So we'll start with, somebody else said, -7. Then what? -5? Uh-huh. Right, and we have to stop at 3, of course, yeah? Because one more would be 5. That's going beyond 4. How many items did we get here? What is n? 6. And you don't have to write this out, right? I mean, like, so we wrote it out because I want to make sure everybody was seeing what numbers we were picking and not picking. It's helpful to me if you do write it out, because that way if you sort of like maybe overlooked -1, I'd know, hey, they were doing the right thing, they just missed one. Make sense? But you could also count these in your head, so to speak, right? You could go -7, -5, -3. We could do that. All right, so part A, proper subsets. What would they be? All right, so 2 to the 6th, which is 64 subsets. And part B, how many proper ones? 63 that are proper subsets. I think that's our last one because this one was my scratch slide. Yeah. Any questions on this idea of subsets? All right.